So yeah, today we're going to focus on AI inference performance. Charles Frye is a pretty well-known person in the GPU space. He works for a company called Modal. I'll let him introduce himself. He has a PhD. We should call you doctor. Yeah, sorry, doctor. Yeah, Dr. Charles. He'll be talking about, so I actually first stumbled upon Charles on it's called CUDA mode. Actually, I think it's now called GPU mode to make it a little more inclusive. It's not called TPU mode, it's called GPU mode, so it's still exclusive a little bit, but getting closer. Maybe accelerator mode would be the next step. But
Oh boy.
Charles built something called the GPU Glossary, which is helps kind of demystify. And I think this came from a blog post that I can't seem to find anymore. That was like, I'm tired of not understanding the NVIDIA stack or something.
Yeah. That's a private blog post that became
Hilarious.
the public GPU glossary. Yeah.
Got it. Got it. Yeah. So I always thought that was funny because it sort of represents the way that I think all of us feel about, the NVIDIA stack is like, this thing has evolved over the last 25 years and no one quite understands the whole extent of it. And actually that's the focus of my book is trying to make sense of it. And so I've certainly referenced your glossary quite a bit. Um, Yeah, I think I'll keep it pretty short there, and then I'm going to talk about agents and specifically some MCP things. I'm going to talk about DeepSeek and some of the slick things that they did that kind of relates to AI, or that certainly like relates to the AI inference and their multi-latent attention. But yeah, what was the other thing I was going to say? Oh yeah, and then next month we'll also have similar. I think we've got a speaker from a company called Modular, and yeah, Charles, you know those guys, right? Like
Yeah.
yeah, like Chris Latner and stuff. So we'll have them on talking about AMD and NVIDIA and how they've built this language and this environment called Mojo and their Max. It's called the Max Runtime Engine. They just released something I think last week called Mammoth, or maybe 2 weeks ago called Mammoth, which is their Kubernetes serving platform. So it's similar if you're familiar with like LLM-D, or if you're familiar with like Dynamo, the NVIDIA Dynamo project. These are all Kubernetes native projects, and so hopefully we'll be getting some good tips on that next month as well. Charles, man, take it away.
Yeah, thanks for the intro, Chris. A lot of kind words. Hope I can live up to them. So what Chris wanted me to talk about some recent work that we put out, kind of a follow-up to the GPU glossary he mentioned that was sort of demystifying the CUDA stack. So this new thing that I'd like to share with you all is the LLM Engine Advisor, part of our LLM Engineers Almanac. I guess there's no standard terminology in this field, so what I'm calling LLM engineer, maybe Chris would call an AI performance engineer. We'll come up with a good name for it in the end, hopefully. So the idea of this is this sort of broader LLM engineers almanac project is to try and like collect up a bunch of useful resources for people who are trying to run their own language model inference, something that is increasingly becoming an actually good idea as opposed to something you would just do like climbing Mount Everest as like a because it's there and because you want to do hard things for some reason. So the like couple things that power this like shift over from getting AI from an API to like running your own. One is that there's now actually like an embarrassment of riches for models. So I just click this list of models here. We got Qwen, the 2.5 coder, and the latest Qwen 3 series. We got DeepSeek, we got Llama, we got Gemma, we got the models from Mistral. Like, we got a lot. And I don't know if anybody else remembers, like, torrenting the Llama 2 weights or whatever when they came out or when they were leaked. Or the Llama 1 weights even. Yeah, that like there was a time when there was nothing, and now there's actually like quite a number of things you might want to run. Um, there's also been an improvement, a substantial improvement in a lot of the like open source software for running these things. We've got SGLang, we've got vLLM, and we've got NVIDIA's entry into this series, TensorRT LLM. So now where we previously, it was like, oh yeah, you'd probably have to roll a bunch of this stuff yourself. It'd be slow because you don't have any of the optimizations that the frontier labs have for serving their models, or that proprietary model inference servers have for sharing their models. Now you have, like, you can just, pip install vLLM, and that is going to bring along a bunch of optimized kernels from NVIDIA, optimized kernels from Neural Magic slash Red Hat, and then like a serving framework around them with things like page detention, etc. So now you can run things pretty quickly. The problem then becomes like, you want to run something, you've maybe convinced yourself that this open source model does well enough on benchmarks, or you've run it like using Hugging Face transformers in an offline mode, and you've benchmarked it and you see the performance is decent. And then the question becomes like, can you serve this to hit your latency objectives and like get a throughput that hits like some cost bar that you have? Like, what's the minimum cost you could serve at, or what's the amount of effort required in like engineering time to get to the point where you can serve at a certain, like, certain requests per second, which translates into a certain dollars per token, since you're paying usually by the hour for your infrastructure, and you're getting tokens out. So tokens per request per second, you get dollars per second, then you end up with tokens per dollar. So built this, ran a bunch of inference benchmarks to figure out basically how much this was going to cost, to help people who wanted to use our platform to run language models, help them figure out, like, could they get something, could they serve a model like with their latency objective for a certain amount of money. So the idea of this advisor, we got this kind of Mad Libs interface up here. Okay, I want to serve this model. I don't care what framework I want to use. I want to get the last token to clients in under 3 seconds, 10 seconds. Yeah, that one's a little bit harder. I expect on average 128 tokens in, 1024 out. Let's switch that around to prefill heavy, so 1024 in, 128 out. And then we'll show you a bunch of configurations that we tried from TensorRT LLM, SGLang, and vLLM. Looks like vLLM is generally getting better latency, lowest latency, and highest throughput in this particular case. So yeah, vLLM is the best was the best thing that we tried on this, and it looks like with this one, oh yeah, you can get up to pretty high tokens per second, or requests per second here. This is at requests per second is here on the x-axis, latency here on the y-axis. So in time to first token. So yeah, we're getting eventually to, oh yeah, let's change it to time to last token, since that's what we set our service level objective to. So yeah, we can, like, we're still well under 10 seconds, and we're at 20 requests per second. That's pretty cool. And over here we got like a little bit of code. You can copy it and run it to try it out. This will get a hold of infrastructure on Modal and start running a server. Just do like a little quick check if you copy that and run it on Modal. And then you can just deploy it on Modal, and now you've got a service that should hit these throughput numbers and those latency numbers measured from clients. So yeah, so that's the tool. And hopefully folks who are interested in doing their own self-hosted LMs, their own self-hosted AI systems, find this useful for, capacity planning, cost estimation, and kind of making that build versus buy decision. Like, should you just keep like paying an API provider or using OpenAI, or can you take the llama's reins in hand and run it yourself? So cool. Plenty. Want to give lots of space for questions if people have specific configurations they want to see or are interested in. Yeah, not sure how you do questions. Looks like there's a lot of stuff in the chat, Chris.
Yeah. Yeah, I was going to wait till the end, but if you're ready, we can start pounding you with questions.
Yeah, perfect. Yeah, so questions coming in here. Have the vLLM and SGLang and NVIDIA folks reached out to you poking holes in these benchmarks? Yeah, so we did. I mean, the responsible thing to do when benchmarking and making, claims that you're going to promote on social media about a piece of software is to reach out to people and talk to them. And so we didn't reach out to the NVIDIA folks because we aren't making super strong claims about TensorRT LLM here. The like little bit of nuance here is that we aren't tuning any of these engines. We're just using their out of the box configuration. And TensorRT LLM is very clear that like our out of the box settings are not good. Our out of the box settings are like minimal, simple, highly compatible, maybe. They don't even have page detention turned on by default, I think. Uh,
Really?
yeah. So TensorRT LLM, we didn't feel like we were making super strong claims, and so we didn't reach out to them directly. But with vLLM and SGLang, they say like, oh yeah, our out of the box configuration is pretty decent. You should run with it. It's a good place to start. So we did reach out to them, and I think they, yeah, sort of, yeah, they had some thoughts. So yeah, Michael Goen, contributor to vLLM, committer to on vLLM, had some thoughts about sort of how to arrange the benchmark, how to talk about it, which was helpful. And then talked briefly with some folks at SGLang as well. And they, yeah, they, you know, there was like one case in which we thought like vLLM was faster than SGLang, and they were like, "Oh yeah, we think that should never be possible." Like, send us some traces. So we don't have any results on that front. But our like overall, the other reason I think our overall point, which is here, we have like if you're not in addition to the advisor, we got some like other documents in here, an executive summary that sort of talks about the bill versus buy decision and then gives some high level things about uh, uh, the frameworks. So scrolling past the bill versus buy to the which open source LM engine should I choose? Like our basic point was that like vLLM and SGLang, like out of the box, like there's a 50-50 shot basically which one's going to be better on your workload for the workloads we tested. And so, we didn't come away with like a strong, immediate one of these is better. That's the one you should use. So I don't think anybody was too mad. Um, so would like to accumulate like really optimized configurations for specific workloads as we go, like get contributions from the teams or from people in the community. So I think you shared the stopwatch benchmarking code link. That's a place to go if you're interested. Happy to give credits if you want to run the benchmarks yourself, reproduce them, find more optimal configurations, and then submit them so that we can share them with everybody. We'd be happy to sponsor that work, and great way to get your own workload included in the benchmarks, and so cause the providers of the engines to make them better over time. um yeah, so there's something in it for you as well. I'll just quickly point out that the last page here, this how to benchmark thing, talks about our benchmarking strategy, and also like kind of talks about how we think you should think about performance, how you should think about like which numbers you should measure and how you should think about those numbers. What like time to first token matters in these cases. Inter-token latency is helpful for this workflow of capacity estimation, and all that stuff is in here. And we've done a lot of sort of solutions engineering on this, but the thoughts in this article come from our conversations with vLLM, with SGLang, and folks on Dynamo, and then a number of LLM people running LLM inference on Modal. um cool. We got I think there may be some questions in addition to the ones from you, Chris. Maybe some questions from Zevi or others.
Yeah, Sevi, if you want to post your question here, let's see. It's tough to do the raise hands thing because we got so many people, but if you could
Mhm.
just type it out here. Um,
Um, I'll answer couple of these questions while we wait for folks to type stuff out if they so choose. So how can we reproduce these results in our own environment? So hopefully this code snippet it's not like code identical to the one we used in the benchmark. So there might be a little bit of divergence. If you notice that, let me know, and I'll try to, sort of make this better. The benchmarking code is available if you want to like directly run the exact thing that we ran. So that's github.com modal add/stopwatch. This framework here, stopwatch, this is what we do. So like this should give you the exact same performance. But then this is meant to be like this has a bunch of like fancy bells and whistles because we're basically spinning up a vLLM service, not an LLM server running vLLM. So what I mean by that is like we can literally just by changing the client requests, spin up a new model on like different hardware with different configuration parameters just by changing like client requests, which is awesome for a benchmark, but dubiously useful for a production service. And so like it's not the code that we share because we want you to take that and like get it running in a production service. And ideally these benchmarks, yeah. Yeah, we want to align, make sure these benchmark results actually work, are reliable for capacity planning if you go and change the code a little bit. Okay. Then oh yeah, looks like we're gonna get some questions in the chat shortly. Great.
Yeah, that's why everyone was like trying to raise their hand. It's some new default Zoom setting where they like disable
Course.
chat. I have to figure that out.
Great.
Anyway, chat's
Yeah,
on now, folks, if you want to start it. Sorry about that.
great. Yeah, how can we use our own models on Modal? Super quick one. Here you can see that the way we bring in a model is like it's just a model repo string. And that is something that pretty much like Hugging Face model repo is something that basically every inference server has to understand. So like literally we're just passing the model path as like a command line argument. And so, you could change that to point to your own weights on Hugging Face if you store them there, or you can change it to just like a path like on the remote machines. There's some like demos of how to do that in the modal docs. So should be basically um should be like extremely easy to do that. We show how to use this like model cache feature with modal distributed storage on volumes. That like if you want to use a custom model, you'll that you don't have on Hugging Face or whatever, you'll want to put it on a modal volume as described in our docs. Um, yeah, so let's see. Question from Bender. Could you speak a little bit about the difference between vLLM and SGLang? Yeah, there's not a lot of daylight between them. Like they're both like aiming to do the same thing, which is to be like be easy to install high performance LM inference engine, the like open source solutions like made by people in the same lab in Berkeley, like two different projects. I'd say SGLang is like second to market, and so they have some benefits of sort of moving second, and so being able to just like not do some of the things that vLLM did early on when the space was less figured out. So it's maybe a little bit cleaner in code and a little bit simpler. Um, they claim higher performance than vLLM. vLLM tends to claim sort of like equal performance. That's what we see in our benchmarks. Hard to tell, lots of configuration knobs. SGLang by default has faster startup times because they don't do torch compilation. They don't do CUDA graph capture. So things start up quickly, but you can turn on torch compilation and CUDA graph capture. And then with vLLM, you can turn off torch compilation and CUDA graph capture. I think that suggests like vLLM is kind of bought in on torch compile and SGLang is not. Like there's like a GitHub issue where they're like they say like, oh yeah, SGLang says, oh yeah, we're trying to like kind of beat torch compile performance without using torch compile. So we'll see. Like that's kind of depends on whether you think that project is going to be the solution for people writing high performance stuff. Um, Torch compile helps vLLM have like a broader support Like vLLM was generally first to market with features before SGLang. Like not just that they were the um, you know, earlier framework, but also like when we put our benchmark out, I think SGLang had not yet merged Qwen 3 support. I can't remember there's the source of truth here is what I write is not what I'm yapping about right now, but what is written here in this executive summary. So yeah, SGLang, there was an issue that of that ran it that we couldn't run the Infor Quant of DeepSeek v3. We were running into some CUDA OOMs with Qwen 3 tier 35B that we didn't resolve before release. vLLM things were like smoother, apart from a little bit of like configuration trouble, but they had like all the models we wanted to run on all the like on all the hardware we wanted to run. I don't think we share any publicly yet. We're still like getting the numbers finalized. But we did run vLLM on Blackwell B200 GPUs, and vLLM had that released already. Um,
Yeah, have you
yeah,
guys
so
tried like the NVL72 setup?
no, we haven't done the like super big scale up domains that NVIDIA offers. In part because we're trying to offer this like abstraction layer over the like cloud
Right.
resources, and it's pretty hard to abstract an NVL72, you know? Like it's like a pretty like specific piece of hardware. And it's not something that they'll like, there's no market for them, right? Like we kind of aggregate demand on one
Yeah.
side and then go to people who have supply on the other. And yeah, so there's like a bunch of sort of like technical and like socio-technical or economic things that make that challenging. I think a lot like it's also notable that like NVIDIA does push those like this like rack scale solution that they have, but you see a lot of people deploying like 8x
Yeah.
things like just connected by InfiniBand. So I'm not sure how much that's actually been like taken up in the market. Who knows what's going on inside of the like frontier labs? I get the impression that they aren't actually using that, but yeah. So we're kind of we're I would say we're trying to be like just behind the people at the frontier of what's being done open source and like try and solidify it, get these nice solid benchmarks, make it super easy to run. And I would say that NVL72 large NV link domain stuff is beyond the frontier of what people are doing openly.
Yeah. Do you folks have plans to support like CoreWeave and Lambda Labs and those folks by any chance?
Yeah, I guess our view is that we're explicitly trying to abstract
Yeah.
away a
Got it.
specific location. Yeah, I guess CoreWeave and Lambda Labs would be a place to go to get those like large scale up domains. Um, yeah, we work with a number of cloud providers. I think like we want in order to make something abstract, it needs to like support a really rock solid iron abstraction boundary. And a lot of the neo clouds are like the robustness just isn't there yet. And then we have a bunch of, kind of requirements in order to be able to produce the like super high quality like DevX that we offer to people that not every neo cloud can support. And that so that is, those are the kinds of technical challenges we're you know working with the neo clouds to resolve so that we can offer more of them. Um yeah, I see a lot of questions coming in. Let me answer some quick ones. Daniel Rollis, have you seen other good observability framework for LLMs and or data observability framework? Yeah, so this is focused on performance. I haven't thought as much about like observability as I used to. Like that was kind of my big thing. I worked at Weights and Biases and spent some time thinking about like training observability. Um, but yeah, I'd say with LLM ops, it's like all still pretty open. It's like probably you should start with simple things like spreadsheets, Jupyter notebooks, etc. And then once you understand what the hell you're trying to do, like then look around for a framework that can accelerate it or build it yourself. If you've got great data infrastructure, if you've got like a great data engineering infra team that builds good internal tooling, they'll probably take the workflow that you've got in a spreadsheet or a notebook and turn it into a better internal tool than what you'll be able to buy from people in the market today, because nobody really knows what they're doing, I think, with LLM observability. Um, yeah. But yeah, there are people out there, Weights and Biases Weave, Langsmith, Brain Trust, Datadog, and Honeycomb have their own tools. So, to some extent, it's like if you're already using one of those existing solutions, maybe take a look at what they've got. Um, if you could say a few words about running very heavy jobs that need many tokens in context, what do you recommend running it? Yeah, the more stuff you have in context, the more beneficial it's going to be to run on really big, latest and greatest GPUs. That will give you more memory to to store that context and to run on bigger batches. Once you get to a long enough context, you're maybe compute bound even, even on a fast GPU running on such a long context. So then batching becomes a little bit less important. But in general, you're gonna want you're gonna want the hot hardware for that. If you have many tokens in context and you want to have a short latency for your decodes, you probably need disaggregated prefill. So it's less about improving throughput and more about making sure you can control the latency at which tokens show up for users. Disaggregated prefill means like separate GPUs for context, like producing the KV cache, and then for doing generation. So vLLM, SGLang, they support this. We don't have any benchmarks on it. There's no default configuration for it, so there's no clear thing for us to benchmark as default, but you can check those out. Let's see. Does Modal work on TPUs? No, we don't have TPUs. Again, it's like we want to be abstracting cloud resources. TPUs are pretty concrete. We find there's not a huge lift. And not a ton of demand for TPUs. The software stack is not as fully featured if you don't work at Google. So you can't use the internal tools. And then it's like hard to find people who are like trained in it, know how it works. Not that GPUs are easy to find people, but it's at least feasible, especially if you're willing to pay a lot of money. With TPUs, it's like nearly impossible. You got to wait to see who from DeepMind is left without starting a new startup and hire them. We don't have it, but if like that becomes the standard for people, we are in a GPU platform. We're a Linux containers platform, and Linux containers can run on TPUs. Yeah. Binayak recommended what architectural patterns recommended to process data in offline or batch mode, dynamically spin up LLM inference services online and shut them down once the offline processing is complete. Man, my recommended architectural pattern is to use modal.com. So Modal is designed for auto scaling, and we have super fast cold boots. Like our containers start in a second or two. And so that's often enough to be able to run an auto scaling service live. It's a little challenging to scale to zero with LLMs because it takes about, I don't know, 60 seconds minimum to spin up a vLLM or SGLang server. But if you're doing batch offline and the thing is you just don't want to pay for it all the time, then you want to like spin up, run, and then spin down. Modal will do that that's like basically what's being shown here with this snippet here is like one way to do that. I also have this this demo of running like a super high throughput Mistral on the human eval data set. So this is like a classic batch case. You want to run the model to generate code on this human eval code benchmark, and then run the code to check whether the code runs. And that you can do that at super high throughput with serverless on-demand resources with like a relatively small amount of code. We wrote the initial version of this in like literally one day when I got excited about the large language monkeys paper. Yeah, similar question for Ming Hao Hu here. Offline inference platform like working with Spark, you want to get max throughput without caring about latency. Yeah, in general, I would say it's you probably don't even need the OpenAI API compatibility layer if you just want to like send a bunch of requests and get completions. So in that case, it'd be even simpler than the code. But yeah, Modal should be able to Um, run that pretty effectively. And like throughput, really like, yeah, you have like per replica throughput, but with like the solution to get like maximum throughput total is to increase the number of replicas. So especially if you're not cost sensitive, you could just blow out in parallel and Modal will get a hold of all the GPUs you need to do that. Up to like, up to 10 on the starter plan, which is free, and then up to thousands if you get on our enterprise plan. So hit us up if you're interested in running on like thousands of H100s, H200s, or B200s. Tibor asked about benchmarks and resource constraints environments, like running DeepSeek in H100 GPUs. So yeah, that actually is our only DeepSeek configuration, is the like int4 quant, because we only have H100 results in this initial release. So yeah, we were able to get like almost a request per second at 128 tokens and 1024 out. We switch over to 1024 in, 128 out. So heavier on the context, you can see we get higher throughput, especially in latency insensitive cases. And actually, if we say first token in under like, I don't know, a minute, so latency insensitive. Yeah, I guess same thing, up to 7 requests per second. Um, okay, so then let's see. I see online Modal runs on OCI. How that cloud provider decision was made, if you currently plan to use other clouds. So yeah, we don't only run on OCI. We just run a lot on OCI because the infra is good. It's like, yeah, it's trustworthy. It's like yeah, has we get bare metal instances which have some small performance benefits. Yeah, we also run on Azure, AWS, GCP, and then a couple of these neo clouds. So yeah, yeah, Oracle, I would say, or if you are willing to like figure out how to use it and go through like a slightly less fully featured interface, less less worn down, less polished by the many hours of lost engineering time. Then Oracle gives you some really great stuff. And that actually they have like the best free tier of the hyperscalers, by the way. Like you can run a little server in the cloud for free on OCI. Forever. Like Amazon gives you like a T2 Nano or whatever for free for a year or two. Oracle like promises, free forever. Um, so that's like that's kind of nice. Um, oh
Any
yeah, Daniel had a follow-up question. Have you seen good observability for data consumption output of LLMs? Yeah, I think adding just like putting like a little Grafana at and God, why am I blanking? You got your Grafana dashboard, Prometheus Grafana thing on top of this is super straightforward. We use the metrics endpoints directly in our benchmarking code. We just like grab numbers and store them in like a little SQLite database. But what you'd probably want to do, not for benchmarking, but for production serving, would be like a little there's like a Prometheus compatibility layer in vLLM and I think also in the others. And then now you've got your normal that will give you observability on things like token counts, right? Like requests per second, latencies, all the things we're talking about here. Um, that's not going to answer these like quality questions. I guess this is an AI performance engineer thing. So we're trying to focus on just that stuff and not the like model quality and model correctness and user experience. That is what I was kind of talking about in my first answer, which is yeah, just Bit tricky, probably build it yourself.
Great. Um, on a personal question, how did you choose that color hair?
Oh, yeah, years ago I like started dyeing my hair for fun. It was changing like every couple months when you have to re-bleach it. So then you can just change the color. And I was like,
Yeah.
change the color every time. And then uh I kind of liked this tennis ball color, so I stuck with it for like a year. And then people started to be like, I recognize you, but I don't know
Yeah.
where.
Yeah.
Hair, are you on Twitter? And I was like, oh yes, that is the color of my hair on Twitter. Oh no, I'm stuck with this forever. If I want anybody to recognize me. So yeah, I've had it since like Weights and Biases days. So before joining Modal and before becoming an NVIDIA shill. But turns out two of my favorite companies that build the infrastructure that let me do cool stuff, both like the color green, that's also my favorite. So yeah.
Yeah, that was my guess, is that it was, yeah, because of the NVIDIA green, but okay, there was more to
Green
it.
is green is the color of growth, money, GPUs, and the modal serverless infrastructure platform, which are all things I think are great.
If you had stayed at Weights and Biases, you'd be at CoreWeave right now, huh?
Yeah, it's
Antje.
true. That would be a fun, interesting adventure. I'd be working at a publicly traded company, but yeah, I'm happy to be back on the rocket ship ride at the
Yeah.
beginning. It's a fun phase. So I look forward to Modal's eventual
Yeah.
publicly traded phase to get that experience.
Yeah, I don't want to keep you. Thank you so much. I think there's like a few other questions here about like open telemetry and stuff.
Yeah, I'd say open telemetry for AI is like an unsolved problem. Open telemetry for performance is just open telemetry, right? Like just use the regular OTel stack. I'd say Langsmith, weights and biases, weave. If anybody remembers the illicit composition explorer from ancient times of 2023, like all of these are very OTel influenced because they're very trace oriented, right? And that's at least that's the like first thing I think of with OTel. It's like the hard part of the spec is the tracing, right? Um, yeah, that all that stuff is inspired by it, but it turns out that you can't really um, the difficulty in predicting system behavior as inputs change due to the nature of large language models, which is to say that they are giant piles of floating point numbers where tokens come in, tokens come out. You can't explain it. That limits the utility of a classic like observability or telemetry stack on behavior and on yeah, I think that's what Daniel's asking about with data or information observability. I'm not that when I hear the word data observability, I think they're talking about what I would call, yeah, like LM ops or LM observability or AI observability, which is to say, like knowing observability, following Charity Major's excellent definition, is that you have enough stuff collected from production serving in your like metrics, charts, etc., that you can debug the system from that without having to run it. And that works great for traditional software because humans wrote the code, humans designed the machines, and you can just like you can reason your way to the behavior of the system. And it's hard. Not everybody knows how to like reason about the behavior of x86 assembly or the like behavior of a a Paxos layer for consensus, but like it's in principle possible. And that is, I think, yeah, that's I think the that's the like the intellectual bedrock on which observability for software 1.0 systems are built. But these like, mushy neural network predictive model, generative model, systems, like we don't actually know what it will do on different inputs. And so it's much harder to achieve true observability just from like logs and traces. And so I would say that's what prevents there from being an easy answer to the like data observability question, as I understand it, or the like open telemetry for AI problem. And so I think honestly, it's a place for technical innovation. It's a great thing if you're an early PhD student or somebody looking to start a new startup. That's the kind of problem you should think about solving. Or if you're working at one of the frontier labs. It's a hard problem to solve while you're also trying to solve, some like humdrum or more classic engineering problems of hitting a latency goal at a certain cost, or making an LLM engine go faster. Um, but yeah, I gotta run. Thanks so much for having me, Chris, and thanks for a bunch of really excellent questions, everyone. These were great.
I'm sure I'll see you soon. We tend to be at the exact same conferences in the exact
Yeah,
same tracks every single
yeah.
time. So
We're still so early, despite the fact that it feels like it's been an eternity since the release of
yeah,
ChatGPT. Like you go back to the history of personal computers, and we're still in the like MIPS Altair era, the IBM clone era that everybody's forgotten about entirely. So yeah, it's a small world, and we'll be running into each other in it. If you run into me, uh, like please do say hi. And it's a small enough world that my DMs are still open on Twitter. Happy to answer questions if you post them there. That's Charles_IRL on Twitter. And I'm also on LinkedIn, but a little slower on LinkedIn than on Twitter. Word.
sweet man.
All
Yeah, have a
right.
good week, bud.
Take care, Chris. Bye.
Yeah. All right, folks, let me switch over here. I'm going to share my screen. That was awesome that Charles joined us there. Hang on, I think I shared the wrong thingy. There we go. All right, so let me share this. Let me make sure y'all can see it here. And I think we have Antje on. Did Antje join? I know Antje had a meeting. Let me see here. Let me promote Antje here in the background. Antje, you are being promoted to speaker here. Say hi. Let me make sure you can go on camera. Hey, your co-host. Why don't you pop on and say hello?
Hi, everyone.
There you are. All right, yeah, so Charles was just on, and I'm gonna kick into my talk. I'll probably talk about another 10, 15 minutes over, but I'm gonna keep recording, and if folks have to drop. Antje, what's going on with you? What are you focused on these days?
Agents. Is anyone working on anything else?
Yeah, MCP. Yeah, you were at the AI Engineer World Fair last week, right? Or was it
Yes.
2 weeks ago?
I think it's already,
Oh yeah, you
like
actually
2
gave a
weeks ago.
keynote.
I did. A lot of stuff, great things happening in the Agentic AI space.
Okay,
So yeah,
we
looking
can
forward
get
to
you
hearing
on.
how we can increase the performance here.
Yeah, and then you guys have like the Strands, Strands SDK and stuff. Maybe you could put a link in the chat for
Yeah,
MCP and agents that works natively with like AWS and Lambda. And your keynote, from what I remember, actually showed how to build a MCP server with a Lambda function in just a few lines of code. That was kind of cool.
that's right.
And then you guys are part of the MCP governance body or something?
We joined the MCP steering committee. Yeah.
Steering committee. Okay, sweet. And then you're also taking a look at A to A, which is really cool too. Okay, sweet. All right. I don't want to keep you, Antje. I know you're busy there. But yeah, thanks for joining. I think you're like between two meetings now, from what I remember. Let me get everything ready here, and I'm gonna start my talk. So my talk's gonna be pretty technical, although I'll try to keep it coherence. So let me make sure you could see. Let me see here. Yeah. Okay. Looks like you could see. Yeah, Antje, funny story. I totally forgot to turn on the chat, which you remind me every month to do. And I forgot to
Oh
do it for like
no.
the first 15, 20 minutes. Okay. Yeah. Hey, everyone. Chris Fregly. I do have this book coming out. This thing's a beast on my in my Google Doc. This thing is about 1,000 pages, so I have to work with the folks at the O'Reilly Media to figure out what to do. I'll make sure you all get all of the information, all 1,000 pages in some capacity. Part of it might be a book, it might be 2 books, it might be 3 books. I don't know, but the content is pretty much all done. I just need to work out how to get it fully reviewed, which it's in the process of being fully like reviewed right now, and then get these things out. So if you look at the Meetup link as well too, inside the Meetup description, there's a link to the GitHub repo, which has the code. That's we've got CUDA code in there, PyTorch code. We've got GPU kernel optimizations, all kinds of fun stuff. So this talk in particular is about agentic AI and specifically inference systems. So why do we want to focus on inference in this world of agents? Well, yeah, obviously faster time to response, better end user experience. We can serve more users with the same amount and cost for the hardware. These GPUs are expensivo, as we all know. This is probably my number one thing that I speak with folks about these days is, why am I only seeing 40% GPU utilization? And, what am I doing wrong? So I spend quite a bit of time on these things, tuning these like inference servers. There's a lot of folks, particularly like enterprise folks, that are starting with vLLM and then either forking it or trying to make small optimizations specific to their use cases. But let's talk about some of the bottlenecks. So pretty much in a modern agentic system, there are all kinds of bottlenecks. Pretty much every single layer has a bottleneck, from the UI, from the type of user prompt and prompt caching and things like that, which is kind of jumping into the solutions. But there's to the actual agent handling itself in like the AWS world. This could be, or Lambda function not being efficiently developed. So the book goes into some of those details, and actually, I think this talk might talk a little bit about that. But if you're deploying it with Lambda or deploying it with Kubernetes, there's some things you can do. Down to the data store that's actually storing the memory for the session, for the for the stateful session that these agents might be using, all the way to the tools themselves. And then, of course, the LLM. So this talk specifically focuses on the LLM and like the inference side of things. All of the other performance optimization that you have been doing throughout your career still applies. It's just the actual like inference engine side, there's some pretty like unique things, especially with the interactions with GPUs, which we'll be talking about. So I'm going to talk about some of the DeepSeek optimizations that came out, that surfaced. After their release, they open sourced a bunch of stuff and wrote some blog posts and things and papers. And so I'm going to cover some of the stuff that I thought was cool, that specifically applies to the inference side of things. I'm also going to talk about vLLM and NVIDIA Dynamo. I don't have too much on SGLang. I've actually used vLLM more than I've used SGLang, but I'm starting to see like SGLang popping up more and more. So we'll talk about some of those. Also talk about CUDA and PyTorch optimizations, and specifically the newer Grace Blackwell chip and this supercomputer that they call the NVL72, which has 72 of these Grace CPU plus Blackwell GPU super chips, is what they're commonly like referred to. So what's cool about Grace Blackwell is you have all of the memory that a CPU has, right? Like the addressable memory, combined with the sort of limited GPU memory. And they're calling that unified memory, and there's ways to optimize that. So like stepping back a bit, I want to encourage folks to, when you sit down to optimize, to think about what's called mechanical sympathy. Now, this is an older term, I think from the early 2000s or something. This famous person, Martin Thompson, actually coined it. He has a whole blog dedicated to this, and he was, when he first described it, was referring to this race car driver Jackie Stewart, who was famously not just a driver, but he was also like a super mechanic, and he really understood the inner workings of his car. And so he would be driving and he would be giving feedback and, working with the actual like engineering team to tune the car. And so, this is something that you should think about. Like, you should really like try to understand your surroundings, and surroundings here being the GPU hardware, the network, the storage, and this is all stuff that the book goes into heavy detail. Yeah, and so the term here really is like co-design. You'll probably start to hear this more and more now that you've heard the term, but you want to co-design software and the algorithms with the actual hardware capabilities, and vice versa. And so what you're probably not seeing, because it's not very public, I guess, is that folks at like NVIDIA, folks at like AMD are working really closely with researchers, with these like AI researchers and these frontier labs, and saying, hey, what is the bottleneck for these like specific LLM algorithms? Okay, it's the transformer. We're going to come up with something called the transformer engine, which is optimized for those types. So just keep that in mind, co-design. Specifically, DeepSeek actually had a pretty unique situation where there were U.S. export controls. So, oh yeah, and so DeepSeek is a company out of China, and because of like U.S. export controls, those folks couldn't get the full power of the Hopper H100 and H200 GPUs. They were given a sort of limited capacity, like a little bit lower compute, like a little bit lower, I believe, like memory bandwidth. And so DeepSeek was forced out of the scarcity to actually bring about, like innovative solutions here. And so they released something called DeepSeek v3, which is the base model. And then there's DeepSeek R1, which is a reasoning model that's really, on par with some of these leading frontier models from OpenAI and Anthropic. And so let's talk about some of these. And so, yeah, off of DeepSeek's GitHub, this comes straight out of their like GitHub repo. They have 5 or 6 of these innovations. By the way, the one that I'm not really gonna, well, actually, I think I'm only talking about those last 2 right there. But the one that really doesn't apply as much to the inference is this Fireflyer file system, 3FS. So DeepSeek actually created their own file system because, and which is optimized for like distributed training and the ability to load data quickly. So they went as far as actually building their own file system to work around some of these limitations. But really, the few that, or the 2 that we'll talk about today, will be these optimized parallelism strategies. And the talk earlier talked about like disaggregated prefill and decode. These are 2 separate stages within a single like inference call, and ways to actually tune these separately. So we'll talk a little bit about that, and then we'll also dive a bit deep into how they use mixture of experts and some specific things here for their inference system, which is actually based on vLLM. They forked it. They had adapted it to their own environment, which actually uses Huawei chips out of China on like the inference side. So pretty scary diagram here. It's actually quite simple. It's just a bunch of like linear algebra. This is specifically the prefill and then decode phase. And what we're doing here is right down the middle is the KV cache, key value cache. And this is critical. So the handoff between prefill, so a like request comes in, goes through prefill, this KV cache is then populated, and then the decode phase uses the results from that like prefill that's now stored in cache memory there. And so these are 2 separate phases. These are actually very different like compute memory characteristics. The prefill phase is very compute heavy because it's huge matrix by huge matrix, right, like computation. So that like requires a lot of flops. On the decoding phase, this is typically a vector times a matrix. And there's a lot of data movement with the decode phase, much heavier than compute. And so the reason that there's lots of memory is because when you're decoding, that's where you're actually generating the tokens. That's where you need the full model. And if this is, in the like DeepSeek case, it was roughly 670, I think the new one now is 685 billion parameters. And so that's a lot of memory that has to move into the GPUs to then do this token generation, okay? So just know that the two separate phases have distinct characteristics, and they typically are tuned separately. They're scaled differently. You could even use different types of GPUs, ones that are optimized for compute on the prefill, and the ones that are optimized for like memory bandwidth, for example, on the decode. It's not exactly the best way to do it. You typically want to use a homogeneous, GPU cluster. You want to use the like latest GPUs, which would be Blackwell or the Grace Blackwell 200s these days. That way you can actually sort of change the configuration dynamically. And I just finished up that chapter last week where you can tune and sort of shift workers in your cluster from the prefill phase to the decode phase if suddenly you get a big spike of decode. In those cases, you want to have the same compute so that you can sort of plan ahead and like use those workers in the best possible way. Okay, so here's just another view, prefill, decode, and generating the tokens. All right, so DeepSeek R1 and DeepSeek V3 are a mixture of expert like models, and specifically they use something called multi-latent attention. And that's a different, or that's a essentially a variant of just like generic like attention mechanism, which is used heavily in transformers. And let me see, because I'm kind of running a little bit out of time, and I want to make sure that we cover everything. There's a couple. The key here is that they figured out a way to better like overlap the like communication. So consider. So there's like 32 experts here, right? And that's on the like prefill phase. On the decode phase, they have data parallel experts up to 144. And these things span different like number of nodes, and they're scaled separately. But the key here is that they were able to actually find like a what's called a like dual batch strategy, where they're able to hide the latency of these throughput. So when you're working with a GPU, you've got high throughput machine, right? Like GPUs like lots and lots of data, and you want to hide that like latency, right? Because when you have hardware that's optimized for throughput, you have to optimize and hide the like latency that's actually caused by the like throughput native machine. Okay, and so they are able to do things differently during prefill than they do during the decode phase. There's another point I was going to make on that slide, but I think I get to it here. And so what they want to do is have a separate. So what like DeepSeek does here for their specific like use case is they separate out a separate prefill load balancer from a decode load balancer, and these both of these, and so in blue here and then sort of pink, these are separate workers that are like actually getting these like prefill requests and then decode requests. They share a centralized KV storage, because remember the like KV cache is what's being shared between these two. Okay, and so this actually helps to like balance the load across all of these different workers. Now on the like prefill phase, what we're trying to do is optimize for like balancing the like input tokens. We want to try to prevent hotspots where certain GPUs are like being overloaded, and so they have various like dynamic routing like capabilities that are built into this load balancer that can work around like different hotspots. And so there's a whole lot of like hardware topology strategies that are being used where it's constantly checking which of the GPUs are currently loaded, and can't like keep up with the load, it can then, you know, like route things around to like other network segments also. So these systems are constantly keeping an eye, not just on the like GPU utilization, but also keeping an eye on how saturated the specific network is, how saturated the memory like bandwidth is at these different stages as well. So on the like decode side, we're trying to, yeah, like basically do the same thing, but we, you know, yes, like I said, these are different phases here that have different characteristics. So let me see. What was my point on this one? I built this slide deck last week and just trying to remember what I was like getting at here. Balance expert. Yeah, I think I covered all this. Oh yeah, the other thing to keep in mind too is that there's a way to create what's called right, these like expert like replicas. And what you want to do is have the replicas placed in such a way that you're not crossing between nodes, right? So node 0, for example, has a relatively slow connection to like node 1. And so if you're requiring that like these experts like talk to each other, at some point these experts have to come together and share the information that they have to actually generate the like token. And if you're requiring that that communication travels between two nodes, that's going to slow things down. And so what you want to do is carefully place and schedule, right, like these experts and their like replicas onto GPUs that will minimize inter-node communication. Okay, and there's a whole ton of heuristics and, you know, a whole bunch of strategies on ways to do this and ways to you know, test this out. This comes, I believe, straight out of the yeah, this is based on the vLLM project. I'm trying to think here. So yeah, the request comes in, goes through the API server, goes to the prefill. And then, yeah, I think I've covered all this. Okay, here is the, yes, I mentioned this earlier, I think on the chat about the LLM-D project. So this is actually scaling out the like inference engine across multiple nodes. Now this is a like fully open source project. This is maintained by like the NVIDIA folks, by folks over at IBM. And this is like first-class Kubernetes native. And there you see down at the bottom there where you have the LM cache. So that's where the KV cache lives. You've got different techniques here where you can, you know, route to the different variants. So here you see variant A as the prefill, variant B in this case is the like decode phase. Okay, so I'm trying to not get too deep into the weeds. Let's see, I think that's another view. There's some things you can do here called like KV cache offloading, where you can, so the KV cache typically is stored in a distributed manner, sometimes on the CPU, and sometimes parts of it can even be offloaded to disk. And so there's a lot of different, you know, least recently used strategies and, you know, paging in and out. If you are using the Grace Blackwell chip, it'll, it's not that big of a hit to store it in the CPU memory because the CPU and the GPU are connected. Those chips are connected at like very high speed between and on the same silicon. But let's see, we get to this here. So these are terms that you should know, which is disaggregated prefill, decode, and the ability to scale them separately. There's this term called the arithmetic intensity. And typically you're talking about like an algorithm or a CUDA kernel that you've written. What this means is it's the ratio of the compute flops that are performed per byte that's moved in and out of the GPU from main memory, from the GPU's main memory. And so the goal, and this is pretty much what, well, actually I have a whole chapter dedicated to this, which is how do you increase the arithmetic intensity? And the reason that we always want to do more flops per byte is because we have really fast GPUs on the computation side, but these like modern GPUs still have relatively low memory bandwidth. And so the more compute that like we can do per byte moved, we will like better saturate the actual GPU utilization. This is probably the number one thing when you see that you are only utilizing 40% of your like GPU cores or what are called streaming multiprocessors. It is very likely that you are waiting for memory to come in and out. And the whole book is about trying to overlap the like memory transfer with the compute and network transfer with the compute. So yeah. And then the other thing is like speculative decoding and what's called multi-token prediction. These are roughly the same things. There's some nuance here, but just know that in order to increase the arithmetic, and so those last two bullet points are ways to increase the intensity. And so you can, on the decode phase, you would traditionally just generate a single token at a time. If you can generate speculatively, like multiple tokens, and then do a real quick verification on that whole batch of the speculative tokens, and choose up to the longest token that you got correct, and then drop the rest, on average, you will increase the arithmetic intensity and the overall throughput. Okay. There's some other techniques here too that are used by almost all of these like inference engines, which is, the ability to batch up multiple requests. This is, pure and simple, trying to increase the flops, like trying to make bigger matrix multiplies, and just moving those weights into the GPU like one time and then doing more math. Right, like if you're not using like continuous batching or some form of batching, you will be like moving those weights, the 670 billion parameters, into the GPU each time that you want to generate a single token, which is pretty wasteful. Other things to know is that CUDA has been sort of co-designing. Of course, they both come from NVIDIA. But there's been new hardware that's actually dedicated to solving this problem of the memory movement. There's something called TMA, and that's going to accelerate the actual memory transfer. This is on hardware, and of course supported by CUDA, supported by the PyTorch and these like inference engines also. And what this does is it like basically offloads the memory movement so that the GPU cores, what are called streaming multiprocessors, don't have to do this. So the like GPUs themselves can focus more on compute and then offload to the hardware, to the TMA, which will then move the data at the same time that you are also calculating the actual matrix multiplies. Okay. They've also been continually improving what's called the NVLink, and these are connections between CPU, GPU, and also between GPU and GPU. Also adding things like unified memory. Yeah. So and yeah, like unified memory has actually been part of the CPU, GPU. Part of these NVIDIA GPUs for quite a few years, but it's now become much better because the CPU and the GPU are now on the actual same chip itself. Okay, and so just know that you'll be seeing terms like the NVLink. If you start to explore your system and you start seeing connections going over PCIe, that's actually bad. That's like a traditional like connection when you installed a GPU in your home computer. So like try to stay away from anything PCIe. Try to prefer if you can like an NVLink connection. Try to prefer things like the InfiniBand. So yeah, these are all super critical. Let's see. Yeah, Grace Blackwell super chips. There's like one more thing that I spent quite a lot of time in the book preparing for, and I finished that chapter a few weeks ago, but it's these things called thread block clusters. They're also called CTA clusters because thread blocks are, so threads are, similar to like a CPU thread, but they're really, really lightweight and they run on the GPU cores. And a thread block is a group of these threads. And there's now first-class hardware and CUDA support for what's called thread block clusters. This lets you, and there's something called distributed shared memory, and then there's some native synchronization primitives to keep these threads and the thread blocks in sync with each other. So before thread block clusters came along, you were limited in how much compute that you can do, and you couldn't necessarily cross these cores like very easily, or you could, but it would require some like pretty complex synchronization, not really optimized. So again, as these models are getting bigger and bigger, things like thread block clusters, which is new to Blackwell, by the way, are extremely important to code for. And if you are looking at frameworks like PyTorch, or starting to look around at some of these other types of like inference engines, make sure that they are thread block and like updated for Blackwell. So really, that's where these performance optimizations come. There's the pure sort of flops of these GPUs, but there's a whole ton of other stuff that's required when you're actually doing these computations, and that's going to be memory movement, that's going to be core or like streaming multi-processor like communication, and yeah. So one more thing, yeah, DeepSeek. So this is kind of well known by this point, but I just wanted to highlight it. So yeah, obviously GPUs have a like pretty well-defined memory hierarchy where they have what's called streaming multi-processor registers, which is similar to CPU registers. They have an L1 cache, they have an L2 cache, and of course they have the global memory, what's called VRAM, or sort of legacy. The V stands for video RAM because these GPUs come from a sort of graphics context, right? And so, and as you like progress up, so the like registers basically live on the die. They're super cheap. They're basically free to use, but there's not that many of them. As you go up through the the like two different cache types, the size gets bigger, but they get slower. And of course, global memory is the slowest, but it's also the biggest. So one thing that the DeepSeek folks realized is that they could actually, because of the like access patterns that right, like decoding and the sort of inference right, like workloads use, there's a whole lot of like memory movement, and so they could actually speed things up by bypassing the L1 cache and going straight into the L2 cache. Okay, and so there's this like PTX, which think of it sort of like it's like the NVIDIA GPU. It's their sort of I guess you would call it the assembly. There's actually one layer lower that's called SAS, SASS. That's the true assembly. This is basically the instruction set that you can write this code yourself. And so with this one instruction, they were able to get huge performance gain. And of course, this was not very well documented. They kind of had to hack on it. But what they realized was that by bypassing the L1 cache altogether, and that they could get these chunks going directly into the L2 cache. Okay. And why this is clever is it was reducing cache pollution, which then sort of like reduced the cache thrashing that would typically happen here. This then boosted L2 bandwidth usage and was able to reduce the like global load latency that goes against that VRAM global memory. Huge performance gains, especially for memory bandwidth bound kernels, which is common in the like inference world. Ideal for the read-only access pattern when like loading these weights. Very friendly for the like KV cache itself, because when you're using KV cache, you're not really using the actual L1 cache. So if you bypass it completely, that's going to give you some performance. I think this is pretty much the last slide here. So once again, the term co-design comes up here. We're now extending it beyond GPUs and CUDA, but we're also talking about PyTorch as well too. So all of these have been sort of co-designed together. This is actually, I think, similar to the subtitle of the book, which is rather optimizing GPUs, CUDA, and PyTorch together. So the PyTorch compiler can, fuse together CUDA kernels. This is all with the goal of trying to increase the arithmetic intensity, trying to do more flops per byte moved. Also trying to optimize GPU register like utilization. You could do things like loop unrolling. These are common tricks also that are done in the CPU world, but these are particularly important in the GPU land. And yeah, I think the book goes into much more detail where we talk about the instruction level parallelism, which is sort of related to the loop unrolling, and some other cool techniques. PyTorch also now supports what's called CUDA graphs. And this lets you put together multiple CUDA kernels that are commonly run together. So of course you can imagine the decode phase has the same set of like matrix multiplies and softmax and all that good stuff. So by packaging those up into what's called a CUDA kernel, we can then just launch that single graph one time. And there's a fair amount of like overhead when you're launching CUDA kernels. But if you can put them all into one graph, that'll sort of like predefine that graph. And what like you can do is actually create graphs for different batch sizes. So think of an inference case where you might have dynamic batching where you're doing one, maybe you're doing 2, 4, 8, like 16 requests at a time. If you generate those 5 or 6 different like CUDA graphs, now you can call on those when needed, and you're going to reduce a little bit of overhead. At scale, this is huge performance. These seem like really micro optimizations because it's very small overhead, but at scale, these things add up, of course. And then the other thing too is, the obvious, these GPUs have what's called tensor cores. These are hardware optimized for different floating points. So 16-bit, floating point 8, floating point 4 now. So floating point 4 is not actually part of PyTorch just yet. It does have support for floating point 8 on these GPUs. This is mainly because Blackwell is like relatively new. PyTorch lags behind a little bit. I think floating point 4 might be in one of the nightly builds from the like latest PyTorch. I would have to check that. I don't think it was when I looked last, but it might be now. And then let's see. The other cool thing too is that these tensor cores are separate hardware pipelines. And so you can actually run like an FP16 at the same time in a single cycle from your GPU. Like you can run an FP16 with an FP8 and like an FP4 all at the same time. And so these are the little tricks that the CUDA ninjas, as they're known, can really take advantage of. And if you combine that, so a single cycle within your GPU, if you can run multiple of these instructions and fill up those instruction pipelines, and combined with the TMA for the data movements, this is pretty much as fast as you can get. And so fortunately, all like these tricks have been built by NVIDIA into CUDA, into libraries like Cutlass, CUTLASS. So you don't necessarily have to do all this stuff yourself, but when you are looking through code or trying to figure out if a particular library is as fast as possible, or you're profiling these things, you can start to pay attention to the different pieces that are involved here. Okay, so stepping back, we've got faster inference basically means faster agents. So this is tying everything back to agents. This is going to give you those great properties of being able to serve more users with the same hardware, faster experience. So yeah, and thank you. I actually built this for another talk, but let me just get rid of that. Boom, boom. And let me see. Let me look at the questions here. And I don't have too much time, but let me get to as many as I can. Okay, left is. Okay. Looks like if anyone has any questions, let me know. Yeah, a lot of content, I know. And the book makes more sense of this and kind of gives like a narrative. That's why it's almost 1,000 pages. Is trying to set up all this stuff. But the real goal here was to sort of introduce folks to these terms and things to pay attention to. And the other thing to really take a look at is these different repositories from the DeepSeek folks. These will be difficult to understand if you don't have some of the fundamentals that are described in the book, but you can start to get an idea of where is time being spent. You will hear tons and tons about the like disaggregated prefill and decode. I think I'm finishing that chapter later today. That'll be the last one on inference. I think I have about 4 or 5 chapters dedicated to inference, and then the rest on GPUs and CUDA. So yeah, I'll try to get this shared out. Definitely going to post the video in a few hours once it gets encoded, and I hope everyone found these talks interesting. We'll see you next month. Antje, do you know who's speaking next month? Oh, actually, I know who's speaking next month. Let me here. I think I'm going to do another talk from the book. Yeah. So next month is going to be crazy. There's all of these different inference tuning strategies. So I kind of hinted at them here, where you've got separate KV or like prefill decode workers, and there's ways to. And I talked a little bit. I didn't get too far into it because it starts to get a little crazy, but the ability to change the parallelism strategy. So here we see DP. This is data parallel. You can actually swap in like different parallelism strategies at like runtime, and based on the state of the system, based on if you're getting a lot of like reasoning requests that do a whole lot of decode. Back in the sort of first days of like generative AI, we were doing huge requests and then asking to summarize. So we had huge sort of inputs and then very small outputs. So that would be a whole lot of prefill and not that much decode. Nowadays, we're asking questions that do require lots of decode, lots of thinking chains, lots of reasoning thoughts, and that really puts pressure on the decode. But if like throughout the day you have different patterns happening, you could actually scale these independently. You can do a whole ton of stuff. So I finished that chapter, I think last week or the week before, and that's the stuff I'm going to present in a month. And Antje, yeah, we'll try to get you on too to talk about the Strands API and some of that stuff that's happening. Also, we'll have the folks from Modular on here as well. So they're the first talk. They'll be talking about how to build PyTorch operations. I'll also ask them to talk about their new Kubernetes serving engine that works across both AMD and NVIDIA. So it's called Mammoth. I believe they just launched it. It's pretty cool. So these folks over at like Modular are some of the best kernel engineers that I've met, and we will have some of them on next month to talk about things. So yeah, Mammoth is a Kubernetes-based system here that can do, it's not right now, it's not as full featured as something like a vLLM or an SGLang, but it's supports both NVIDIA and actually supports Intel and ARM, and of course AMD as well too. So, and it works across the different clouds. Excellent. Am I not wearing my Cubs hat? No, I had it on, but I'm going to the gym right after this, and then it gets all dirty. So yeah, thanks everyone. See you next month.